I am Davide Basile, and this is a joint work with Maurice Terbeck, Maxime Cordy, and Axel Legay. The context of the talk is model-based mutation testing. So in particular, model-based testing is a method to automate the generation of test cases by using a formal model of the system. So formal model of the system drives the execution or generation of test cases. With respect to mutation, to model, to testing made directly on the source code, we have that model-based testing is useful, for example, for detecting misinterpretations of requirements or time-dependent interactions with the environment. This kind of problems would be hard to find by working with the source code, and thus a formal model is useful. In particular, mutation testing. The idea of mutation testing is to perform a mutation of the model or the source code in case we are working with source code, and this mutation mimics bugs that are introduced by either the programmer or the modeler of the formal model, and these mutations thus produce a set of mutants, and mutation testing can then be used to either evaluate or generate test cases. For example, for the evaluation, we have that a good test case should be able to detect all mutations. That is, a test should be able to find a bug if a bug exists. And on the other side, we can start from these good mutants, that we will see what they are, and from them it is possible to generate tests that are capable of detecting them, and these are good test cases that are generated. In our case, we are working with time-dependent systems, and we are generating test cases. So those are in italic in this slide. We have the equivalent mutant problem. This is the problem that by applying a certain type of mutations, we may have mutants that are equivalent to the system under test. And in this case, these mutants are ineffective for either evaluating a test suite or generating a new one. So we would like to avoid the generation of equivalent mutants. We are working with formal models. In particular, the formal specification that we use is timed games, the theory of time interfaces. And for example, this is the classical example of a coffee machine where we have a state as 0, a user insert an euro, and this is an input transition. And the clock is reset to 0, and in state 1 we can stay at most 4 time units, but after 2 time units has passed, the machine can output a t, and this is an uncontrollable transition. So in this theory we have controllable and uncontrollable transitions, and in particular controllable transitions are the input and uncontrollable transitions are the output. In this theory we take the point of view of the environment, or in this case the user of the machine, which can control the insertion of coin but cannot control the output of the machine, in this case the t. We are interested in with the first order mutation, that is, we only apply one mutation to the suit. In this particular example, we apply this mutation and we swap the constant 2 with 4 in the mutant. We have now 4 instead of 2. In our theory, we say that a mutant is subsumed, that is a refinement or equivalent. These are all synonyms. In case it has less uncontrollable or more controllable behavior than the suit. And to check the refinement between the mutant and the suit, we use ECDAR, that is a tool for performing refinement checking for this specific formalism. In case the mutant is not a refinement, the refinement check provides a witness, that is a trace that is capable of distinguishing the mutant from the system under test, and this can be used as the test case that will be generated. In this particular example, we have that the mutant is indeed subsumed, and it cannot be used as a candidate for test case generation. This is because in this case we have less uncontrollable behavior in the mutant with respect to the system under test, because for example when the time is 2, the system under test can output the t, but the mutant cannot, so it has less uncontrollable behavior. The mutations that we will use in this talk, in this paper, are those that are listed. So, in particular, we may add or remove a transition, we may remove a state, and we may also have mutations on the time. In particular, we may change the constant of a clock constraint or negate a clock constraint. The next step is to organize these mutations in a featured mutant model, where we have a feature model whose features are indeed the mutations. They are in exclusive OR because only one mutation can be activated, and this enables the efficient generation, configuration, and execution of mutants. This is again the example of a coffee machine, and this is a feature time gains that are similar to feature transitions. The idea is that within a single model, we are capable of modeling all possible configurations. By selecting a particular configuration, we select certain transitions, and certain transitions are not selected according to this feature expression. That is an atomic propositional formula whose atoms are the mutations and the features. In this particular example, when we activate this mutation, we have that V mutate the constant, while when it is not activated, the constant is the same. And the mutant that is in this example can be obtained by projecting the feature time game on this particular set of features that are the T and the CXL mutant for this specific transition. So coming to our contribution, originally for building this feature mutant model, we have to select random mutations as features. And this may lead to family of mutants that are ineffective. That is, all their configurations or their mutants are equivalent and are not useful for generating test cases. The solution that we propose is to drive the selection of mutations to discard those that are ineffective. And this can be performed by using our 12 commandments of model-based mutation testing. So the main idea is that once we have a formal specification and a formal relation that tells us whether a mutant is good or not, we may have formal results that tell us by construction whether by applying a specific mutation we will obtain a mutant that is good or not. And this can be performed statically, so bypassing the refinement checking that requires the execution of the system. I skip all the technical details you can find them in the paper, and I go directly to the list of mutations that are in our 12 commandments. In particular, we can see that the mutation 6 is that this mutation shall not be applied to uncontrollable transition with guard of these forms. And this is indeed what we have done in this example. We have applied that specific mutation. Maybe we can see this better here. We applied this specific mutation to the guard of these forms, and what we obtained is, according to our commandments, is a mutant that is subsumed, and this is not good. This is because we have violated one commandment. One other thing to note here is that the first commandment is more of a requirement. We require that the system under test shall not be redundant. Redundant means that we have dangling transition, dangling states. In general, we don't want to have such model for each possible use that we want to make of this model, whether this will be model checking or model-based testing. So this is more of a requirement rather than a specific commandment. We wanted to evaluate our theory with two research questions. The first one is we want to check empirically if our guidelines are sound. Of course, we already have formal results that tell us this, but we wanted to check them empirically also. And the second research question is that we want to measure the quality of our guidelines, how complete our guidelines in detecting equivalent and subsumed mutants. We measure this in a relative way as the percentage of subsumed mutants that our guidelines are capable to detect. The case study that we used is the car alarm system from Ford's automotive demonstrator in the Mutantes project. The specific model has 17 states and 88 transitions. We implemented a tool that automatically applies the mutations that we have used in our paper and generates all the mutant. And then we check each of these mutant against the suit for refinement by using the tool ECDAR. These are the results of our experiments. We see on the first column, we have all the possible mutations. We have a total of 721 mutants. We see that more than 50% of these mutants are subsumed or redundant. That is, these are bad mutants that are not useful for our purpose of model-based testing. And 326 of such mutants are violating our guidelines. So the first research questions is asked, is answered. That is, all mutants that are violating guidelines are indeed those that are subsumed. So our guidelines are sound. Coming to the second research question, we see that we are able to detect 88% of all the subsumed or redundant mutant with our guidelines, so without checking the refinement. So our guidelines are very efficient in detecting ineffective mutants. Moreover, we avoid the generation of up to O to the 2 to the 326 possible combinations of not good mutants that would lead to fruitless feature mutant model. Feature mutant models whose configurations are all redundant mutants, and these are not good for our case study. So we see how many mutants we are capable of detecting and discarding with our guidelines. So concluding the talk, we presented a technique for identifying effective mutations for real-time systems statically, and as future work, we would like to perform an all-at-once refinement checking of feature time games to check all at once the mutants in our system on the featured time game. We also would like to evaluate test suites in feature time games, and we would like to explore higher order mutations that are mutants obtained by applying more than just one mutation. And for doing that, we would like to exploit the refinement relation between mutants. And this concludes this talk, and thanks for your attention.